Okay, so we are trying to do some problem which will be medium and Google question. Um, let's take this question. This is count square submatrices with all one. Given a m into n matrix of 1 and 0, written how many square submatrices have all one. So we have this matrix and we need to tell that how many of them will have all ones. How many matrices has all one? How many square matrices or matrices has all one? So it has to be of same length and width. Of side 1 we have 10. Of side 2 we have 4. And of side 3 we have just 1. So it is total less. When we come over here we have size 1 will be everything. 2 is going to be just 1. That's it. So constraint over here is um 300 by 300 of them. Okay, so we have about 300 by 300 matrix, of which we have to find out how many matrix forms a square with all ones. Okay, so if we know like suppose we have something like this, and it could be anything, but what I'm trying to tell is that maybe we have something where if we try to find the maximum matrix, then we know that how many inside it of them will be of 2, of them will be 1. They will be just the some formula we have to use, those many it will be. But how do we find whether it is a square or a, a big square one? We have to find out. Like in this case, it is actually a rectangle, but we will only consider this part. We have two squares of size 2, something different. So it could be like we might have one, one, and one. Similarly, we have over here one and one, and same thing over here. So we can tell that this will be 3, this will be 3, this will be 3, and this will be 3. So in this case it is better to know what is the largest, like a rectangle or whatever, like a rectangle of ones. Okay, so Also, if I try to think of a brute force first for it, how it will be, we will try to find ones. So we will go for all elements and we'll check how many of them are ones. That will be for side 1. Okay, side 1, this will be all elements with 1, with value 1. Now if I go to side 2, then it will be mm, I will check that all these 4 of them are 1 or not, like this. Then when I will go to 3, I will check whether all these elements in this 3 by 3 are 1 or not. So um, okay, and if we have something like 4 by 4, how could we check whether it is a matrix of 4 by 4 or not? What will be the complexity then? We'll check for all ones, we'll check for all 2, then 3, then 4, then 5, then 6. Something like this until we have covered into min of n comma m size. Okay, this is a dynamic programming problem, but how are we going to approach it? Okay, let's just concentrate what we are doing with brute force. So in brute force, it is like an 300 cross 300 matrix. First iteration will take 300 300. This will be like, is it not same? M into n. Then next will be like 2 by 2, and we have to check, and we need to check. If we check this all of them, it is okay, and then we check this. So we have actually already checked this part, so we know that this is going to be all 1. We can make something like storing the sum of each. Yeah, we can do that because we know it is only ones that are present in this matrix. So if we try to find what is the sum of this square, it will always be some unique number, and if it is that means it will be some certain number, and is not going to be any random number, so it's going to be some certain number. Like for a square of 3 by 3, sum is always going to be 9. So if the sum, and we know that nothing, it's not going to be more than 1, so if we are getting a sum of 9, it means it is a square of 9, but we need to be checking squares only. So I think this is something like prefix sum we have to store, and at each point, like if I'm over 1 1 1, then 1 1 1, So if I am something over here like I'm at certain point and I try to find that what is I'm traversing to a 3 by 3 right now. So I will try to find what is the sum of this matrix and how I will find that sum. That sum is actually going to be um, sum for this minus sum for this. It will just subtract this part and minus sum this, and then it will actually be like if I'm over here suppose and I have to write 3 by 3, these I have to find. So I will subtract these, I will subtract these, and these are going to be this 0 1 1 0 is going to be subtracted 2 times, so I have to add this. So it's like subtracting 2 things and then adding this thing. And how are we going to store the sum? So sum you can store something like um did some question like this. um okay, if it is just 1 it will be 0, if it is like this it's going to be 2, and then when I'm over here I will just add what was up above it, and then when I'm over here what I'm going to add. Do I need to store like rows and column? No. So it will be this whole sum of upper layer plus whatever is up till now. This is actually going to hold this 1 and 0 sum. So if I add these two, this is going to be added twice. Okay. So is it like this plus this minus this? Let's see. If I'm over here, I already have the sum of this over here, and I try to add this sum. So this sum. So it is actually the sum of this, the sum of this. So we are adding this part twice. So sorry. So now this part is going to be a prefix sum kind of. We can do this because these are all ones. So we can just pre-compute all the values and likewise. So one thing is one thing. Let me just pause. Okay, so we got something like we can add once, then it will be some number. So prefix sum would help us, and prefix sum we could compute, but I don't remember that how to get that, use that prefix sum, how to store. What I'm trying to do is how to store the sum at this position, that sum will represent the sum of this matrix. How do we do that? Is it okay? I can do something like this. When I'm going to a row, I will just keep a variable which is going to store the sum up till now, and in previously computed upper layer, upper rows, I can just use that value to get whatever is the row. So if I have to find a sum at this position, it will be the sum at this position plus whatever cumulative we try to find up till now, something like that. Let's just make that like prefix array. This is basically going to be vector for int and cumulative, no, prefix, and also I will store n is equal to matrix dot size, and m is equal to matrix dot, okay, let's just keep it as row, and this is column, matrix of 0 dot size. Then prefix is actually the number of rows, and vector int, and this will be called, and all places are going to be 0 initially. But we are also going to add something. No, we don't need to add, otherwise it will be difficult to like get what was the value above it and below it when we are trying to find the square sum of some square. So I will traverse it just like that until less than rows. Oops. 1 minute. Okay, until less than rows, and then it will be I plus plus, then column wise. So when I'm traversing a column wise, I'm going to have a variable cumulative that is going to store What's up till now? The sum. J is equal to 0, j less than equals j plus plus. Keep checking this. And now cumulative is equal to cumulative plus matrix. Let's make it as grid, grid, grid of I of j. It's just going to be the cumulative of this row. Okay. And now what is the prefix of I and j is equal to prefix of I minus 1 of j plus cumulative, whatever the cumulative is up to now. Okay, this is okay, and we need to add this constraint like I is like 1, then we will do, otherwise it is just cumulative. This goes well. Now we get a prefix. Now how to find what is now how are we going to traverse? We are going to traverse like we know it will be ones, but when we are at 2 we need to know that um that it's a 2 by 2. Okay, and if it is not, to get all of the ones, it's easy, just the sum of whole. Yeah, like the sum of this whole matrix is 9 plus 1, so it is 10. So side ones are just the sum of this matrix, and for side twos um how could we do for each time is like, okay, suppose I'm over here and maybe this thing is 1. Okay, or suppose I'm over here, just let us suppose, and if we try to find the sum of this whole thing, it will not be a square, so we will neglect that 3 cannot be formed over here. But what about the 2's in this? To find the 2's in this, how are we going to know that it's completely correct? Like for this first row, 2's will already be found out. I am just caring about the 2's at this level. That is, when this row is appended, the 2 will be formed like this and this, like this 1 1 and 1 1 is 1 2, and this 1 1. Rest of the 2's are already calculated when this row was added. So I'm concerned about when this row is added, the 2's that will be formed will be on this row. So there will be like three twos, this, considering this, then this, and then this. So we need to know about all those twos. Okay, so when I was over here, I saw that it was a 3 by 3 and it didn't work. So I definitely must have found a 2 by 2 of this. So I don't have to care again. When I'm over here, I don't have to care about this 2 by 2 matrix. I only need to care about this 2 by 2 matrix. So whenever I'm at any point, I'm only going to at I comma j, I only have to care the squares formed only with this I comma j cells as the right bottom cell element. So it will be 1, it will be 2, it will be 3, and it will be 4, like this. Because rest all at each position we are already calculated, so we don't have to calculate it again. Okay, so when I'm over here and I'm finding a 3 by 3, suppose this is 0. So we know that this is not forming a square of all ones. So we will check for all twos and it's forming. And then we'll check for all the ones. So it is already 1. Okay, so this is what we need to do at each position. And because there will be like around 300 by 300, so it is quite high, means at each position, like if I am at cell value some j value column and I is at a row, so there will be approx the minimum of this ing that many times you have to run at this position. So it will be something like mm, like this 0 0 0 1 0 2 0 3. So all of this in this 0 is going to be the minimum element, then 0 times, and then this case it is like 1 0 and then 1 1 comes, so everything before it will be like 0 and 1 time, and then rest of them will be like 1 1 1 time. Similarly for this it will be 0 1 2 and then rest of them will be 2 times. Okay, so this how it's going to be. So if you consider that this whole thing, it's pretty not very high. I don't know about its complexity. Let's just do the code and we'll find out what its complexity is and whether it passes or not. So whenever I'm at a position, I will try to find all the squares which are possible with this. So let me just write 0 0 0 1 0 2 0 3 0 4. Then it is 1 0 1 1 1 2 1 3 1 4. 2 4. Okay, so it's like this. Now when I'm at this position, okay, let's take this position. So I know it will be I plus 1 at time. When I'm at this position, it will be I plus 1 time, like the squares that could be formed, total number of. So that way we will know that what will be the square that could be formed. So let's move on with each value. For and t j is equal to 0, j less than equals j plus plus. And then when I'm at each value, I'll find what is the square that can largest square that could be formed over here is minimum of I comma j plus 1. Okay, it's just like if I'm over here, like if I'm over 3 comma 2, then I can form something which is or let's take something another, like I am at 4 comma 2, so it can form the minimum is 2, so 2 plus 1 is 3, so it can form just a square that is 3 by 3 and cannot form anything bigger than that. Okay, it cannot form a square of 4 by 4, so because it's limited by the minimum value. Then I will run from from 1 to square. For and I is equal to 0 means it is not running actually. When I'm over here, I will try to find what is 3 by 3. Okay, so it will run like square times 4. Let's just sq minus minus and then c greater than 0 and then sq minus minus. Let's just use this value over here. And now I know that it's going to be the size of square. So this will help me, like if I'm at 4 comma 2, I know I have to find first square I have to find of size 3. So I will, what will be the sum? And the sum is equal to what it will be? It will be pref of I comma j. So right now it is this whole sum, okay, from 0 0 0 to 4 2, but we need to cut this part, so we will subtract something. We have to add constraints also, but we'll add it later. Pref of like I minus sq. So I is 4, 4 minus 3 is 1, so we reach correctly, and then j will remain the same. Then one more subtraction will be done. Pref of like I cut this part. When I'm over here 4 comma 3, and I'm trying to make something of 3 size. Like this is actually 4 comma 4. No, this is 3, so 3 plus 1 is 4, 4, 1, 2, 3, 4. So it will be like this much size. So I cut this part. 4 minus, sorry, it is 4 minus 4 is 0. And I wanted to find of size 3. So if SQ is 3, it's 4 minus 3 is 1. And I will also cut this part, means this first column. So I will get what was the sum over here. It is actually the same row, but J is going to be J minus SQ. Okay, and then one plus is going to be done. That is this is this value. So this is actually pref of I minus SQ and J minus SQ. Okay, so it is a 1 and 0. So this thing I have to add into it because this was deleted twice. And now I will just also add the constraints, like if I minus SQ is greater than equal to 0, only then we do this, otherwise we just keep it as this. Similarly, J minus SQ is greater than equal to 0, then we do this, otherwise 0. And then this will be I minus SQ is. Now what will happen if it is already over here, so there is no element over here. So this is also going to be 0. I minus SQ is greater than equal to 0 and J minus SQ is greater than equal to 0. Then otherwise 0. So this is the sum that I get. Now I can check whether this sum is equal to what should be the value. If sum is equal to SQ into SQ, it means square exists. Okay, sorry, exists. So we are going to just add into our result plus plus, just this much. Fine. So I see if this J is undeclared. Pref of I of J. Okay. Which line? 19. This is giving 15. Let us try this one. It is giving correct. Let's see if it passed the test cases. It passed. Wow. So let's just keep this for future. And okay, it is faster than it's not very good, but let's check what is the discussion going on. Which one is it? TP. The idea is to scan each cell and update the placeholder result variable with the number of squares that can be formed from the currently looking cell when it is bottom right corner of the possible approaches. Line 17. Let's try to understand. Cell list is hence this 0 in any place can disrupt the square combo. Your combo elements depend on all the elements surrounding you. Your combo elements is only as strong as the weakest link surrounding you. Minimum surrounding you. We are going to use that to memorize, and whenever we see one in matrix are going to look the surrounding elements. Yes, we are going to get the minimum value for surrounding elements. Then why? If this one is part of combo chain, then it increases the square size. If this one is not part of combo chain, increase this. What it's doing? In this question, which one? Oh, I tried this problem. Hmm. In this problem, we have of this guy also. In this problem, we can also try like if I am at some position and the grid value is 0, then we know that it is not going to form a square at any point with this as the bottom right guy. Yeah. So whenever we are over here, we can just skip that value. If grid of I and j is equal to 1 is equal to 0, then continue. We not add anything to this result. This is not at all faster, but it's still okay. Memory uses 24 and it's 404 milliseconds. So in this discussion, let's see. dp of means the size of the square with a of ij is the bottom right corner. dp also means the number of squares. How? Means the size of the square. It is actually if a of I and j is equal to no possible square, if I is equal to 1, we compare the size of square, all the three of these. Okay. It's doing same thing as described over here. Oh, it's better code. Let's check this out. So it says that the idea is to scan each cell in the matrix to update the placeholder result with the number of squares that can be formed from the currently looking cell. And we have something like this combo element. We are going to use entry to memorize the combo elements. This is the combo elements. Whenever we see one in matrix, we are going to look for surrounding elements because there is a possibility that it is going to make a square. But whenever we are going to get the minimum value of all surrounding elements in matrix grid, then we are going to add 1. Why? If this one is part of combo chain, then it will increase the square set. If this one is not a part of combo chain, at least it is a cell of size 1 cross 1. Yeah, so it is a good way. Actually, you don't have to find the sum and sizes. It is actually doing something like my solution was a bit long. My solution was doing more of work. This is a better solution. So it is almost like n cubic, like m into n into this size. So it's almost like a cubic um, solution. And over here, if you see, it is what it's doing is like, here's the question, like if something is 1 and its surrounding is like 0 and 0, something it's like this, we are only considered what squares it will form using this, just like in this problem, just like we did. And we are considering what squares can be formed. So it's, if it is 1, there is a high chance that it's going to make a square, some squares it's going to make. But if it is something like this element that is 0 or this element, then it's not possible that this is going to make any square out of this, not even a side 1 square, side 2 square is also not possible, side 3, because it's going to be 0. It's that what the question says. So we are going to skip when it is 0. When it is 1, only then we are going to check that what squares could be formed. So if we know what squares could be formed at each positions, we can easily get, like if we check, this is 0, this is 1, and this is 1 0. So it tells that a size of 3 is not possible. Yeah, so whatever is the minimum of all these, like maybe because in this matrix these are not going to be 0 or something like this, these are all going to be, yeah, it could be 0, but it tells that it's going to form just it cannot form something like 3 by 3, because the next cells are actually um like if all would be 1, okay, it means, it would mean what? It would mean that um this position is able to make a square matrix. This position is 1, it also means it's also going to make a square matrix, and this is also going to match square matrix. And this position, if it is 1, it means it is just combining all these matrices and forming a bigger matrix. So we just add that value. Okay, so it will become like, if this is 1, it is also 1, then we know that we can make of size 2 a matrix of size like size 2 is possible. Okay, so this is actually holding that what sizes are possible. Having a single variable holding the total number of square encountered result. So is it the sum of everything? Update the result whenever you encounter cell with 1. Since we don't create additional grid to hold, space complexity is 1 and the runtime complexity m into n. It's actually the sum of all this thing. Yeah. So let's see, how did you prove? You can try it solving a similar problem, maximal square. This would help you in thinking about for this, and most likely you'll be able to solve this problem. At least that's how I solved it. The way I start to tackle is by starting with the base case. Then I draw 2 or 3 random grids and try to scan the grid row by row as a loop does. My main goal is to figure out how to grow squares from surrounding squares. I try to simplify the process by using as little code as possible. This guy is having all sorts of pilgrims and he's reporting everyone. But this is a good solution. I think it didn't struck into my mind. So actually we are trying to we is doing what is just finding that what size square could be formed over here. So if something can form a size of square 3, this can form a size of square 2. So at each position you are going to update that, and the result is the sum of all those values. Yeah, if you see in this, some values are zeros because these are zeros. So these actually could not be formed anything. So it's just the sum of these all that are taking part are making, because at this point you are able to make two size of square 2. So the answer is actually the minimum plus 1, that is 2. So it tells that it is storing the size of square uh, 2 as well as the number of squares with this cell value. Okay, because you know that if you're able to make something of square of size 1, if you are able to make a square of size 2, then you're definitely going to make a square of size 1 because everything is 1 in it. Similarly, if this is a rectangle square of size 3. So if you are able to make a square of size 3 using this guy, then definitely you are able to make a square of size 2. And similarly, you can make a square of size 1. So if all of these will be 1, then you are able to make a square of size 5. Then you are also able to make a square of size 4 using this cell. Similarly this and similarly this. So this is how, uh, if the count is actually equal to the size, and it's also equal to the number of squares that you can form, which is written over there. It's actually equal to size, it's also equal to the number of the square. So this I think is really good explanation. And this looks like some copy of other question. Yeah, so this is a nice problem. Let's try to code this also. Another approach where we will not be required to make a new matrix. We can just update this grid matrix. And this is a result. go row by row. We don't need this. And grid of I of j is equal to, so if it is 1, we will check its surroundings. Minimum of grid of I minus 1 and I of j minus 1, comma minimum of grid of I minus 1, comma j minus 1, and then grid of I minus 1 and then j. So this, sorry, this plus 1, and in this result I'm just going to add s is equal to res plus grid of I and j. Is it correct? This is, and just using is doing, it's taking minimum of this whole. Yeah, so this is actually like taking the other parts, and you can just have something like I um if they are not, the upper two are there, if there's just one above, then it's impossible to make. So this has to be I and j, only then we will do min, otherwise 0. Let's try this. Yeah, this is n into n m times um complexity. So basically I'm just checking if it is like as mentioned in this, if we have these values I and j, it's just that if I is 1 and its j is also more than or equal to 1, then we can get this minimum. But you might be thinking that what if I have something, I don't have this 1 0 and I just have this thing. So in that case we cannot make a square, right? So we don't care about this j minus 1. Similarly, if we don't have this 1 1 and we just have 0 and 1, so again we cannot make a square of size 2. we can only make a square of size 1. So that square of size 1 is already being handled by this one. So that is why this and operator is to be used. This is a good question. Okay. Yeah, so that's all for today. Thank you. Not viewed, but that was a slow part. It's okay, thank you.